Hi everyone, I'm Harvey Pineda from DCpET 33, and today I'll be discussing how CPUs evolved from simple early processors into the powerful systems that we use today, and how a CPU actually works. I'll be also talking about GPUs and how they differ from CPUs. And finally, I'll also talk about SAP-1 Operations and Programming. This topic is important. Why? Because almost every device we use today, like computers, smartphones, laptops, whatever you can think of, is it all relies on processor architecture that was developed decades ago. And so, let's begin. I'll start with how CPU works. The CPU, or Central Processing Unit, is known as the brain of the computer. It processes instructions, it performs calculation, 1 plus 1, and tells other parts of the computer what to do. Without the CPU, your computer wouldn't function at all. So, the CPU works using continuous loop called fetch, decode, execute. So, the cycle happens billions of times per second. And first, fetch. So what is fetch, no? So think the fetch as if the fetch command for a dog. So basically, it gathers the information to collect. Then in in a better term, so basically the CPU gets an instruction from the computer. Then next, decode. The CPU figures out what the instruction means, like adding numbers, or is it going to compare the values? And next, finally, execute. The CPU performs the action and stores the result. So here, I'm showing you the inside the CPU. So inside the CPU, there are several important components. First, we have the control unit. The control unit acts like a manager. It directs a traffic and tells the rest of the CPU what to do. And next, the ALU, or Arithmetic Logic Unit. Yes, handles math and logic operations such as additions and comparisons. Registers. So next is registers. So registers are tiny but extremely fast memory locations inside the CPU. They store data and that stored data the CPU needs immediately. And finally, we have cache memory. So the cache stores frequently used data so the CPU doesn't have to wait for slower run. And next, the CPU runs on a clock speed measured in gigahertz, or if you're looking for a CPU, you sometimes see the symbol of GHz, so it means gigahertz. So each clock tick represents a chance for the CPU to perform an operation. So the higher clock speed usually means a better performance. But modern CPUs also relies on efficient design and multiple cores. So most modern most modern CPUs have multiple cores. So each core can work on tasks independently. This allows your computer to multitask, like watching a video while browsing the website. Or the great example is the AMD brand. So what I like about the AMD is it has multiple cores, unlike Intel, which focus on um, one application. So they have both pros and cons. But I like the AMD better because it allows me to perform smoother operations while also simultaneously doing other tasks. So all of this happens in nanoseconds. And basically, that's how the CPU works. It fetches the codes and executes instructions at incredible speeds to keep your computer running. Now that we um, Now that we understand how CPU works, let's talk about the evolution of CPU. Alright, so before we had these tiny CPUs with billions of transistors crammed into them, computers were huge, like very huge. So back in 1945, we're going past back the time. So in 1945, we had machines like ENIAC. I think it was, yeah, it was ENIAC. And this was basically the earliest form of CPU. It didn't um like the chip we have now. So it lived on thousands of vacuum tubes, pulled insane amounts of power, and if you want to program it, you literally have to rewire the machine. So it's not great, but it got the things started. So it built momentum to build greater things. So things got a lot better when the stored program concept came along. This idea, introduced by John von Neumann, this let the computer store instructions in memory instead of hardwiring them. That and that's where the classic CPU structure came from. This control unit, the ALU, and the memory, and all of that, we're still using that basic idea today. So fast forward to 1950s and 60s, the vacuum tubes get kicked out, transistors takes over. So this allows the integrated circuits show up. So the CPUs became smaller, cooler, faster, and way more um, reliable. And all of this led to a massive moment in computing history. So in 1971, Intel dropped the 4004, the first commercial microprocessor. A full CPUs on one chip was only 4-bit and made for calculators. But this thing basically started the CPU arms race. As we moved into the 1970s, the CPU got smarter, the clock speed increased, the memory addressing expanded, and instruction sets became more advanced. A great example of this is the Intel 8008, an 8-bit processor that introduced indirect addressing and interrupts. Indirect addressing meant programs could use pointers instead of fixed memory locations, which unlock more advanced software design. And interrupts let the CPU stop what it was doing to respond to hardware events like keyboard input. And a huge deal because it's basically the foundation of modern multitasking. And then in 1978, the Intel released the 8086, and this is where the things get really serious. This chip introduced the x86. So this is what you see on the download section of your application. There's like x64, x86, x32. So basically, this x86 architecture, it was technically a 16-bit processor, but thanks to a segmented memory model, it could adjust up to 1 megabyte of memory, which was massive at the time. Is this complicated? Yes, for sure. Revolutionary? Also, yes. And this wild part is that modern PCs are still based on this architecture today. Now, x86 uses sometimes called CISC or complex instruction set computing. Instead of breaking tasks into lots of tiny instructions, a CISC CPU can do more in a single instruction. For example, multiplication can happen with just one instruction instead of several instead of many things. So basically this saved memory, which mattered a lot back when memory was expensive and slow. So to squeeze out even more performance, the CPU started using instructions for prefetching and pipelining. So basically, instead of doing one instruction at a time, the CPU overlaps the steps while one instruction is executing, the next one is already being decoded. Think of it like an assembly line. This massive they increased performance and became standard in CPUs like the Intel 80386. So, speaking of the 80386, this chip market, this chip market basically jumped to through 32-bit processing. So basically, it introduced the 32-bit registers and the virtual memory and proper memory protection. So basically, this allowed operating systems to multitask efficiently and for sure safely. And which is why the modern operating systems like Windows and Linux are even possible. But as CPUs kept getting faster and faster and memory couldn't keep up, so what did the engineers do? So they added cache. Cache is small, insanely fast memory placed right next to the CPU. So when the CPU gets a cache hit, it avoids slow system memory, keeping everything running smoothly. So today, with today's CPU, the CPU uses multiple cache levels just to keep up with how fast the cores are. And that's how we went from room-sized vacuum tube monsters to tiny, like it can even sometimes fit in your hand. And this is freaking so powerful and even can fit in your pocket. Somehow, they still need better cooling. Alright, so while CPUs are great at doing a few things really fast, next, we got GPUs. So, GPUs are all about doing a ton of things at the same time. That, and that same time is the difference is exactly why GPUs exist. Back in the early days of computing, graphics were handled entirely by the CPU. If you If you wanted to draw a line on the screen, the CPU had to calculate it every single pixel. As display improved, this became a huge bottleneck. So in the 1980s and early 90s, we got basic graphics adapters. These weren't yet the most efficient way, but basically they mostly just handle display output and simple 2D tasks like drawing windows and text. So they work, and thanks to that, we've got now. I mean, think about the VGA cards. The VGA cards are functional but not powerful. But as long it works, then it works, right? So everything changed in 1999 when Nvidia released the GeForce 256, which they literally marketed as the world's first GPU. Why? Because it could perform hardware transformation and lighting. In other words, the graphic cards wasn't just displaying images anymore. It was actually doing math, a lot of it. GPUs are built around massive parallelism. Instead of having a few powerful cores like a CPU, a GPU has hundreds or thousands of smaller cores designed to run the same operation across tons of data simultaneously. And that's that's what we call a perfect for graphics, where you might need to calculate the lighting, the color, and shading for millions of pixels at once. As games becomes more complex, GPUs evolved rapidly. We saw the introduction of the programmable shaders, which allow develop to control how pixels and vertices were processed. So there's this called Blender, which basically you make the 3D objects where there's also lighting, there's also shading, and that. So basically, this unlock realistic lighting, shadows, reflections, and eventually things like HDR and physically based rendering. Then came the big surprise. GPUs turned out to be insanely good at things other than graphics. In the late 2000s, developers realized GPUs could accelerate scientific simulations, video encoding, and machine learning. This led to GPGPU computing with platforms like CUDA and OpenCL. So modern GPUs are absolute monsters and absolute pricey. So They come with thousands of compute cores, and they specialize units like tensor cores for AI, ray tracing cores for what is it for? I think yeah, it was for lighting, so it can look realistic, and massive amounts of high-speed VRAM. And they don't just power games. GPUs now drive AI training, video editing, 3D rendering, and even cryptography. So today GPUs come in two main forms. One is very pricey, and that is a joke. Joke lang. So the two main forms are integrated GPUs built into CPUs. So they are efficient and great for everyday tasks. And next we have the discrete GPUs. This basically the separate cards with dedicated memory built for performance. At this point, GPUs aren't just graphics, or they aren't just things that used to display things at the monitor. They basically make things real. They are the parallel compute engines that just happens to be really good at graphics. And honestly, modern computing would fall apart without them. So CPUs think fast, GPUs think wide, and together they make modern computing possible. All right. So next, let's talk about SAP-1 Operations. SAP-1, which literally stands for simple as possible. So this simple as possible computer, version 1, and yes, it is exactly as basic as it sounds on purpose. So the SAP-1 isn't real commercial CPU. It's an educational processor designed to show how a CPU actually works at the hardware level. No operating system needed and no multitasking. No fancy instructions, just the absolute basics. At its core, SAP-1 follows the same idea as every CPU today. And the fetch, decode, execute cycle, as I mentioned before, and every instruction goes through these three steps. And once you understand this, modern CPUs suddenly makes a lot more sense. So first up is the fetch. So the fetch stage is the program counter, or PC. It holds the address of the next instruction. That address gets sent to the memory address register, and then the memory responds with the instruction and loaded into the instruction register. So then the PC increments, pointing to the next instruction. Simple, clean, and very mechanical. Next is the decode stage. So the control unit looks at the upward part of the instruction and figure out what operation needs to happen, and whether it's loading data, doing math, or outputting a result, or or just stopping the CPU entirely. Then that's basically it for the code. And next we have the execute. So in the execute stage, where the real action happens, that's why it's called the execute. Depending on the instruction, SAP-1 might load data into the accumulator and send values the ALU, store a result, or output data to the display. Now, let's talk about the actual operation. So SAP-1 supports the 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 CPUs, and the instruction set is tiny, but that's the whole point of SAP-1, because it allows you to understand CPUs at the basic level. And the LDA, or load accumulator instruction, takes value from memory and places it directly into the accumulator. So this is how SAP-1 gets data ready for processing. Then we've got add and sub. So add like ADD and sub SUB. So this send data from memory into the B register, where the ALU either adds or subtract it from the accumulator. The result goes right back into the accumulator. No flags, no floating point, just straight up binary math. Next is out, like OUT. this instruction sends what whenever is currently in the accumulator to the output register so it can be displayed. This is basically SAP-1 version of printing to the screen. And finally, there's HLT. So HLT means hot. So this instruction tells the control unit to stop clock. To stop the clock, and which this completely shut down program execution when SAP-1 hits HLT, it's done. No background tasks, no drama. So what makes SAP-1 especially useful is how clearly you can see the data movement. Every operation is just data moving between registers over a shared bus. So this is controlled by timing signals, and there's no magic. Everything happens step by step, mathematically, one clock pulse at a time. So SAP-1 also shows why early CPUs were slow but predictable. There's no pipelining, no caching, no no parallel execution, and one instruction finishes completely before the next one starts. And while that's inefficient by modern standards, it makes learning way easier. So why does SAP-1 matter? Because this tiny simple CPU contains the DNA of every modern processor, and the fetching instructions, decoding opcodes, and executing operations and moving data through registers is all here, just stripped down to the basics. And once you understand SAP-1, the modern CPU stop feeling like black magic and start feeling like, yeah, it's very complicated, but still, you are able to know what's running it or how it runs. So next, let's talk about SAP-1 programming. So you might think that didn't we, didn't we just discuss it? No. So, well, there's a difference between SAP-1 Programming and SAP-1 Operations. So, although they fall under the SAP-1, so basically the SAP-1 Programming is what you write. And SAP-1 Operations is what the CPU does. So, what are they really doing? No? So, they're closely related, but they're not the same. So, SAP-1 Programming is about creating the program that runs in the CPU. Alright, so if SAP-1 operations are how the CPU works, then SAP-1 programming is telling the CPU what to do. And fair warning, excuse me, so this is programming in hard mode. And SAP-1 doesn't run Windows, Linux, or Mac, or even an operating system at all. There's no compiler, no keyboard input, and definitely no Python or Java. So when you program SAP-1, you're writing raw machine code and you're placing it directly into memory by hand. And every SAP-1 instruction is just 8 bits long. It's the 1010101 and just 8 of them like this, parang ganyan. Then every SAP-1 instruction um is just how they are, no? So the first 4 bits are the opcode, which tells the CPU what operation to perform, like load, add, output, or halt, like what I explained earlier. So the last 4 bits are the memory address, telling the CPU where the data lives. So when you see something like 0001 and 0100, that's not random binary. That's an instruction saying, "Hey CPU, load the data, load the value stored at memory address 4 into the accumulator." So the programming in SAP-1 always starts with a plan. You decide the program what should do. So like adding two numbers, then you assign the memory instructions and you assign the memory addresses for both your instructions and your data. So there are no variables or loops. No, everything. So everything has to be laid out perfectly from the start. Once the plan is set, you translate each instruction into binary. For example, LDA4 becomes 0001. That's 301 and then 0100. Add 5 becomes 0010 0101, and so on. These binary instructions are then manually loaded into memory one address at a time. When the program runs, SAP-1 executes instructions sequentially, starting at address 0. It loads the instructions, decodes it, and executes it, and then moves on to the next one. So there's no branching, no jumping, and no second chances. If your memory layout is wrong, the CPU will happily execute garbage. No way. So eventually, the program reaches the HLT or halt instruction. So this tells the control unit to stop, clock, and that's it. A program is finished. No background tasks, no cleanup, just pure hardware silence. So what makes SAP-1 programming so valuable that it forces you to think like the CPU? So you're not thinking in terms of function or logic, you're thinking in registers, memory operations, and binary instructions. And once you understand this, higher level programming suddenly feels way less magical. SAP-1 programming is basically the reason assembly language exists. And assembly is the reason modern software works at all. So it's the foundation, stripped down, slow, and extremely unforgiving. And honestly, if you can program SAP-1, every other form of programming feels easy. I actually tried it, and just 1 hour in it, I watch reels. So from room size machines like ENIAC to modern CPUs and GPUs with billions of transistors, the evolution of computing has been driven by one core idea: finding faster and more efficient way to process information. CPUs evolved from simple sequential processors into powerful multi-core systems, while GPUs emerge as massively parallel engines. And knowing that it is really designed like this to handle graphics and high performance workload, so it is not magic. Okay, it's not magic. So by studying SAP-1, you can start from there. We strip all that complexity and see that foundation of every modern processor. SAP-1 Operations shows how a CPU works. So through the fetch, decode, execute. I've been saying this all over through the video, no? So sorry about that. But it is really the primary concept you have to remember. So I guess medyo napahaba yung explanation ko, no? Pero it's just my way on reflecting on this kinds of topic, because for me to really reflect is I have to really know to explain it well now. So I realized that computers are not just fast machines, but systems built on system and logical steps. So learning how CPUs work through the fetch, decode, execute cycle, and studying SAP-1 helped me understand what really happens inside a processor. It showed me how software directly controls hardware at the most basic level. So understanding the evolutions of CPUs and the role of GPUs also made me appreciate how modern computing relies on both speed and parallelism. So I guess this is really important, and it's not just a guess, sorry, but I understand that it is important to know, learn, and how they were built on the first place. And for sure, in the future, this might be just the foundation and very the most basic stuff you can learn. And for sure, because of AI and innovation, advanced technologies in the future, You'll never know. But I guess, no, I predict we're getting there. I think we're getting there. And yes, understanding these basics removes the mystery behind modern hardware and shows that even the most advanced technology is built on simple logical steps. In the end, modern computers aren't magic for me. They are proof that we humans have come so far, from sticks to these nano chips. And honestly, once you understand how they work, that's when the real magic starts.